Hello. In this video, I will present some aspects related to thermodynamics and statistical mechanics related to the two previous videos about can you burn paper with moonlight? And instead of using moonlight here, we will use sunlight because it's going to be much easier to make these arguments. And you have many interesting aspects and interactions between the problem we looked at earlier based on geometric optics and thermodynamics and statistical mechanics. So what's the setup? We have a sun that will emit some light in all directions. And what we want to do, if we remember, we want to concentrate using some system, the light that comes here, into a very small area. Hopefully, with the goal of increasing the temperature to above the temperature at the surface of the sun, which we saw is not possible. So now we'll see how thermodynamics prevents us from doing so. So the first thing is we have to see that the sun emits some light, and the sun can be considered a black body. So a black body is a body that emits light according to a certain spectrum, and that spectrum only depends on its temperature. And the sun will emit that light, and that light will be concentrated on the surface, and that incoming light will heat the surface. So radiation by the sun with our intermediate system and then our surface can be considered as a way of transferring heat between the surface of the sun here and the surface of our object here. Now we know from thermodynamics that the increase in temperature, in entropy, given by a change, an exchange of heat dq is equal to dq divided by the temperature of the object. So let's look at our setup. The sun is really hot to start with, and we have a temperature here, the temperature of the sun, which is greater than the temperature of our object here, the temperature of the object. So if a certain quantity of heat is produced by the sun, there will be a certain decrease in entropy. So we remove heat from the sun, the entropy of the sun will be reduced. And after a while, the radiation that's been produced will arrive to our surface and will increase the temperature, will deposit heat on the surface. And if we look at a very small amount of time during which the surface doesn't increase in temperature too much, we will see that the entropy of the surface will be equal to the same heat that's been emitted that we took and we concentrate here, divided by the temperature. But since this temperature here is smaller than the temperature of the surface of the sun, the heat is the same, we see that the entropy of the surface will increase by an amount greater than the decrease in entropy that was produced here. So delta S at the surface of the sun is smaller than delta S at the surface of the object. And as we all know, the second law of thermodynamics states that the entropy of a system, here sun plus the object plus everything that's around here, but the entropy of a process cannot decrease, and so everything is fine. Now let's see what happens. Let's say that for some manner you succeed in transferring enough heat that this object now is hotter than the surface of the sun. So now we have this, and that would imply, during using the same argument, that we have this. So what happened? We decreased the entropy. We had some light that was emitted, and then the heat was transferred to the new object, but the entropy of the difference in entropy caused by the deposition of that heat was smaller than the entropy that was lost during emission, and that means that the total entropy of the system would decrease, which is forbidden by the second law of thermodynamics. So just by thermodynamic arguments, we can see that we cannot transfer heat from the sun to our object and get a surface temperature here that is hotter than the surface temperature of the sun. So that's the first aspect I wanted to discuss. In the next board, I will discuss statistical mechanics aspects of the same problem. So we will just treat the same problem. Now we've treated it using optics. Now we've looked at it using thermodynamics. And now we will, in the next board, look at it using statistical mechanics. Now I will just present two different ideas related to statistical mechanics and this problem. The first one will be, if you look at the first video, there is a link to that first video below. We saw that some researchers have been able to concentrate sunlight and achieve a power that is larger than the power of the light emitted at the surface of the sun. And we saw that this was not a problem because the conservation of étendue had something related to the index of refraction of the medium in which light was propagated, and this does not contradict the law of conservation of étendue. But what about temperature? Well, if you have some surface, some body that emits light according to the black body radiation spectrum, we have that the power emitted is equal to the area of the surface times the Stefan-Boltzmann constant times the temperature to the fourth power. So for a given object, the area is the same. This is a constant. So the power emitted by the object goes to the temperature to the fourth. But the trick here is that you would imagine that if the power emitted here is 63 watts per square millimeters, and in some manner you achieve a concentration, I think in the paper that was 72 watts per square millimeters. Well, you would think that since there is more power incoming here, when you get to equilibrium, the power incoming here will be equal to the power outgoing. And if the power here is larger than the power at the surface of the sun, you will imagine that the temperature's got to be higher by this law. But the trick is that some very little known fact is that this constant here depends on the index of refraction. And how does it depend on the index of refraction? It depends on the index of refraction because it depends on the speed of light. I will not do the whole derivation, but just to give an idea of how we arrive to this, in statistical mechanics, we suppose that we have some body, some cavity, and you've got electromagnetic waves in there. And since we have a closed cavity and we quantify the electromagnetic field, the field wavelengths cannot be anything. They have to be all multiple of the width, if you want, of the cavity. That's the same as having a pipe, an organ pipe. There is only some notes you can play with the organ pipe. You have the fundamental frequency and the harmonics. So if your pipe is tuned to emit sound at 440 hertz, you would have 440, 880, and so on. But you cannot, using that same pipe, emit 600 hertz. That's not possible. The same thing happens when you want to enclose light or an electromagnetic field, if you want, inside a cavity. And here, the wavelengths that are allowed depend on the dimensions of the cavity, but when you get this Stefan-Boltzmann law, you sum over all the wavelengths. And so you sum over the wavelengths, and we know that the wavelength is equal to the speed of light divided by the frequency. And using this formula, we can get some power because we know that photons have a certain energy that depends on their frequency. The energy is equals to the Planck constant times the frequency. So when you sum over all the possibilities here to get your total power, so how much radiation you can fit in there at equilibrium, you get a dependency on the speed of light and to get the frequency. But if inside here the medium changes, and if you have a vacuum, you have a certain wavelength, you will have certain frequencies that are allowed. But if in here you put a different medium that doesn't have an index of refraction of 1, let's say you put in water, well, the frequencies that are allowed will change because the speed of light changes. So these frequencies will not be the same. And when you do your calculation, you have to take that into account. And that's how the dependency on the index of refraction of the Stefan-Boltzmann law comes into play. So since in the paper they achieved this power, but it was inside some material, it wasn't projecting, like using a lens, projecting onto some piece of material that was exposed to air, but it was instead, they had this, their light was coming in, and they had a way of concentrating the light, but inside here you had a very high concentration. But here you're inside the material, so the power that's emitted at a certain temperature will be higher than it would be otherwise, and everything balances out. So this whole thing about being able to achieve higher power concentration, radiation concentration inside some material doesn't allow you to reach the temperature that's higher than the surface of the sun, which is consistent with our thermodynamic argument that we presented earlier. And the last thing I want to present is another manner of saying how we can think about conservation of étendue using statistical mechanics, and this will be on the next board. Okay, now I will present how we can think about conservation of étendue from the point of view of statistical mechanics, if you want. And to do that, we will use what we call Hamiltonian optics, which is a topic that's not very often taught. But you probably have heard of the basics of this optics, of the Hamiltonian optics, by the fact that we often presented that light obeys the principle of least time. So what is the principle of least time? Principle of least time says that light will propagate from a point A to a point B using a trajectory that minimizes the time it takes to get from A to B. And how can we write that mathematically? We can say that the action, we call this thing the action, we call it is the integral of dt from point A to point B. So we are here, A, B, and here it can be anything, it can be mirrors, lenses, different media of different indices of refraction, optical fibers, whatever you want. And what this says is that light will propagate so that the time it takes to go from here to here over some trajectory here in space is minimal. And of course, if you look at this in free space, the time would be minimal when the distance traveled by light is minimum, and you get that the light traveled in straight line in free space. And you can also use this to derive the law of refraction, Snell's law of refraction also. That's something that's often done in elementary optics course. But you don't have to do it with media of separate indices of refraction, and you don't have to stop there and say, okay, that's a cute thing, and we don't do anything else with this. What we can do is we can write this as the integral from A to B of n, the index of refraction, over c ds. So just the time taken by light to go over a small distance ds is equal to the speed of the light times the distance. Now, usually in this type of optics, what we do is we have, for example, propagation in, I will draw it in 2 days and then we regenerate to 3D after that. You will see that this light propagates, let's say, around the x direction, and it will propagate, let's say, this way. So what we will do is we will consider x to be the independent variable and y to be the dependent variable. And light can go this way, it can go in straight line, can do anything. So that ds here would be equal to the square root of dx squared plus dy squared. It would be equal to 1 plus dy dx squared root times dx. Just basic differential geometry here. So now what we can do is, if we generalize to more dimensions, we can say that this is equal to the integral of 1 over c n the square root 1 plus x1 point, the derivative of x2 square root dx3, and point that the dot notation refers to the derivative with respect to x3. So we've written our element of length in this manner, and using this we can do the exact same thing that we do in classical mechanics when we derive the equation of motion, and we do the Lagrangian and the Hamiltonian and all the tools of statistical mechanics and the classical mechanics that are based on the Hamiltonian or Lagrangian principle formulation can be used to obtain results for optics. Notably, here we can define, I will just make some room. We can define a momentum in the direction k as being equal to the partial derivative of the Lagrangian, which is L, that's what's inside our action here, with respect to x dot k. And this here, this momentum is basically an indication for a light ray of the direction at which it's propagating and at the speed at which it's propagating. And we can get that the momentum vector is equal to n times ds over ds, which means the small increment in position divided by the length of that increment. So this momentum points towards the direction in which the light rays are propagating, and it gives us all the information along with the position to know what's happening in our system. So when there's light propagating in the system, we know that at every point x, where there is light, there is a momentum vector. And basically this is very similar to what we do when we consider classical mechanics, and then we can use all the tools that are based on classical mechanics to obtain interesting results. And one very interesting result will be that, if you remember, in classical mechanics, when you have many particles that are in some space, and we look at what we call the phase space. So the phase space is basically, I do it in 2D here. The phase space is, imagine that you have a particle that's moving, and let's suppose, for example, we have a particle moving on a straight line. So this particle will have a position x and a momentum px. If you have, and then you can determine what is the state of the system simply by stating where you are here in that phase space. Because we know that once we know the position and the momentum, which gives the speed, and the equations of motion, then we can predict what happens to the system in the future using our equations of motion. So here, what we can do is, here I drew it in 2 dimensions. Of course, you can have it in more dimensions. If you're using 3-dimensional space, the phase space will have 3 space dimensions and 3 momentum dimensions. So it's going to be some 6-dimensional space, which of course I cannot illustrate on the blackboard. But if you have many light rays in a system, just like we had before, you see we had rays that were coming from the sun and they were moving along, and we did things with them and tried to concentrate them. Well, you can picture the effect of the system by trajectories in the phase space. And there's a theorem in classical mechanics that says that the volume of some trajectory is conserved in phase space if there are no energy losses, like here. That's what we have with our idealized transmission of light rays. And it's called Liouville's theorems. And basically what it says is that if somehow things evolve, the system evolves, you cannot lose volume in phase space. That means if, for example, you have something system that's contained within this box, and later it's contained in a box that's narrower in the position, it will be wider in momentum. Because the volume of this region of phase space is conserved, and it becomes this volume. So there is always a compromise between position and momentum. But if you remember what we had with the conservation of étendue, it was the same. We have that the étendue was equal to the area, the surface over which light, the area of the surface of through which the light goes, times omega, which was the solid angle sustained by the light. And solid angle can be seen as the momentum, because the larger the solid angle, the larger the spread in the momentum space, because light will go in different directions, so you will occupy more of the momentum dimension in the phase diagram. And here the surface area, well, it's simply the surface area, how much of the space portion of the phase diagram you occupy. So basically here it would be, in this thing, you would have some spread here in omega, if you look at this 2D diagram, and some spread in the position direction. And if you reduce one, you will increase the other one. And that's how you can get from the principle of least time to the conservation of étendue using all the mathematical apparatus of classical mechanics. Of course, I didn't do all the details. You can look into it if you want in many textbooks. The idea here was to present that all these things that we looked at from geometric optics also have counterparts in other parts of physics, which I think makes this problem very rich, because it gives a lot of information, it gives a lot of links between different parts of physics. That's it for today.